Dzień dobry Państwu na konwersatorium po majówce. Ufam, że jeszcze tutaj niektórzy przyjdą. Przepraszam za mój głos. Welcome everybody to our faculty colloquium. Today we have a guest, Dr. Darko Donevski, who is presently a fellow at the National Center of Nuclear Research, Department of Astrophysics. And he made a PhD in astrophysics and cosmology 5 years ago, 2018, at the University Aix-Marseille in France. And then he was a postdoc at CISA in Trieste, in Canada. And then finally he came to us. He's a group leader here. He's still affiliated with CISA, Trieste, and with NCBJ. He's involved directly in taking and interpreting data of James Webb, and we hope to have a very, very exciting talk on this. Floor is yours. Thank you.
Thank you very much. Can you see me? Can you hear me well? I hope you can see me. Thanks. First, thanks a lot for the invitation. Some time ago, I was hearing my colleagues listening to the talk of our dear French professor, François Combe, and it's a pleasure to be here to deliver a talk of this very hot topic in the modern science right now, which is this, as you can see, beautiful and actually the largest space telescope, which is called James Webb Space Telescope. And today, because there are a lot of different science branches that you can investigate with this beautiful instrument, I'm going to focus on one specific part of its investigation, which is evolution of dust in galaxies, and especially in the very early universe. Oops. No. I killed this. Okay. So what we are going to talk about today, you can see some small content advertising different topics covered by today's talk. And if we want to start, so basically we have to understand why we are so excited and why we, as an astronomical community worldwide, is completely involved starting from the last July when the first data from JWST start coming to our databases. Why we are so excited to work with the data and to explore more using JWST. Not so long time ago, which is in principle starting from the 1990s with the launch of the other huge space telescope, which is still active, and it's called Hubble Space Telescope. Astronomical extragalactic community started exploring the wide world of galaxies in the different phases and times of the universe. And one of the most beautiful and the most, let's say, the most famous investigations of that kind was in the small, for the small patch of the sky that you can see. How can I point? Nope. Oh, doesn't work. This one. Yeah. Okay. So, I hope you can. Well, anyway, if you see the pointer, fine. But we'll try explaining even without this. So you can see this small square in the center of this image, which is what was back in time, like 30 some years ago, proposed deep program with Hubble Space Telescope. And after that, small, what's supposed to be an empty part of the sky without galaxies seen in previous generation of instruments, Hubble delivered actually you will see an amazing world of galaxies, of more than several thousand of galaxies inside this small patch of the sky. And this area is actually only 1/30 million of the whole sky. So this is like a very tiny part of the whole sphere that was observed with very deep Hubble observations. And what astronomers found was something like this. So you can see by eye a whole orchestra of galaxies of different colors and shapes. And later on, people started delivering different tools to understand the evolution of these objects. So what was the most important takeaway message from this first generation of Hubble surveys? That even if you just take small patch of the sky and go very deep with Hubble observations, you can uncover galaxies of different kind and spread over different cosmic times, from very local ones to very distant ones. And if you want to zoom in a bit to see how this world can be resolved with these Hubble observations, you can see you will have something like this. So you can have, in a very small beam of your observations, different galaxies filling this beam with different shapes, different morphologies, different sizes, and galaxies experiencing completely different formation and evolution from their start to their later evolving phases. And what was the outcome and what was basically the physical message from these early Hubble observations was that, okay, so it is not enough if we only understand the world of stars that are actually emitting that light that Hubble is capable to observe, but also we have to understand what is going on with the molecular gas. Because in our theoretical books and what we learn in our bachelor studies and what was written from early years of astronomical explorations is that how actually stars are made is because of the cold hydrogen gas. And these two things are kind of very tightly related. So basically following the life of star formation in these galaxies, we can project and we can follow the life of what is called interstellar medium, and the cold gas component is very, very important component of this interstellar medium. But okay, this is of course very simplified, and this sketch you can see it's like just to reflect the very simplistic picture that was expected for these early years of investigations. But as always in science life, this simplified picture are actually in reality more complex. And just to give you a glimpses of how the evolution of stars and gas in galaxies can be complex, and this interlink between the two presented in one of the most famous large volume cosmological simulations made to date, which is called Illustris. It's a large team of scientists, one of the best simulations that are explaining a lot of observed behaviors of the universe. And you will just see on these two panels how the galaxies that are interacting basically in the center of this image, how they project on different properties as you can read from the top, like their stellar mass, star formation rate, specific ratio between the two, and on the right side you can see what is happening with the gas once they start interacting and falling into massive clusters. So it's a big crescendo of processes that is very hard to even track in simulations, and you can imagine that this kind of evolutionary sequence for some of these galaxies, it's almost impossible, or actually impossible to directly trace with telescopes. But what we can do with telescopes, we can observe a lot of galaxies in with different surveys, with different telescopes on different frequencies, on wavelengths. And then we can apply some statistical methods to connect the same population, like the evolution of the same population over cosmic time, and then to uncover if we are lucky enough to uncover the life of that population. So, but to do this, we have to observe with different instruments in different cosmic times. So we have to apply one instrument that is capable of observing galaxies that are, let's say, spotted very soon after the Big Bang, but then to somehow, from theoretical predictions, make the whole path of their evolution and to find how this population of galaxies will look like if we observe them in the local universe, if they are still present there, let's say. And this is how the investigation of the searches for the most distant galaxies come to the game. And this small video will just explain in few words what are the aims of this exploration. Basically, this is written by our colleagues from the University of Leiden and STSI in Baltimore. And they explain how searching for specific spectral features in the optical images observed with Hubble Space Telescope, you can actually track how distant is a certain galaxy. So if you look at the upper panel, you can see some number that is called Z, which is a redshift. And you can see like that different colors are representing different filters, starting from the shorter to longer wavelength ones, like moving from bluer to the redder colors. So those that are redder, and if you observe nothing in the other filters, it will tell you roughly the redshift of that particular galaxy, and the more redder ones is giving you the higher redshift, like the higher distance. Because why? Because these emitting photons are completely absorbed like leftwards of the certain point, and then everything that is on the left side is called break or Lyman break, and everything that is on the right side will give you some estimate of the distance of that galaxy, which is a redshift. And this is how Hubble started producing the first quantitative picture of the distances of the observed galaxies, and then we use these different observations in different filters to infer some physical properties, for example, stellar masses of these galaxies or their total star formation rates and so on. But the problem with this investigation is that you have to be very patient, but also sometimes lucky to find these very, very distant sources, like the one that is called GNZ11, because it is the galaxy observed at redshift 11, which is like just several 100 million years after the Big Bang. And you will see how what is the look of that galaxy in Hubble imaging. So this is nothing really spectacular, like a red blob with some bright emission inside. And until this year, this guy was the most distant discovered and confirmed galaxy in the universe. But what astronomers predict and what we kind of, let's say, anticipated by combining our theoretical knowledge is that we expected that the early universe is more rich with these galaxies like this one. And to do investigation of this kind of guys, you cannot just rely on Hubble telescope, so you have to push these reddest filters a bit more towards the longer wavelengths, right? Because if you go a little bit on the infrared side, starting from, like in the electromagnetic spectra, starting from UV optical and then reaching the infrared part, we can now complement this world of galaxies with another, let's say, window that is allowing us two amazing things. So the first one is to extend these filters that I showed you in the previous slide, so that you can push a bit more to see more distant guys like this one. But also infrared has an amazing aspect allowing us to learn about the thermal emission that is emitted in the infrared wavelengths. And the thermal emission of galaxies is actually coming not from cold gas, but from dust. And you can see this is a sort of like a sketch what is our current knowledge. So you will see the galaxy Xeon 11, it's this tiny red spot, the rightmost in this diagram, and some other galaxies that are pointed in this picture. And you will see the present time is full of galaxies between redshift. If you read the redshift on the upper axis, and you see how many translates to billion years ago in the lower x-axis, you can see what is roughly the amount of time when these worlds are detected with Hubble. So, for example, the one at redshift 11 is just 400 million years after what we believe that was a Big Bang, right? And with this we started another new revolution in astronomy, which is now available with JWST. And a lot of journalists, a lot of people who are doing outreach are saying, yeah, JWST is like an amazing instrument. It pushes like all our limits. We are discovering some unbelievable things, blah, blah. But OK, why is that? Like, what is really specific about JWST? So the first thing first, common mistake when even among the astronomers is that so far Hubble was actually the largest space telescope. It is not true. So the largest one was actually the Herschel Space Telescope, launched more than 10 years ago by European Space Agency. And this guy had the specific role of observing the world of dusty galaxies, like these very infrared bright worlds. And actually, with this Herschel Space Telescope, we discover that the world of galaxies is not just beautiful and completely, exposed to our views by the light, unabsorbed light coming from the young stars. But on contrary, Herschel found that there are actually a lot of galaxies in which dusty cloud is surrounding these complexes of the young stars that are born in these star-forming galaxies. And then emission of these galaxies can be observed instead with Hubble. It can be observed with infrared instruments such as NASA Spitzer telescope or ESA Herschel telescope. But the problem of resolving what is the particular contributor of that emission is quite hard, because as you can see here, this is the same beautiful view that Hubble Space Telescope allowed some time ago. And if you just observe the same area with far infrared telescope, like if you want to observe the dust emission surrounding the same region, you will have some messy and very unclear view of some bright spots in the thermal sky, which is this a big circle there. So this is the same view of these galaxies here, but this is seen by Hubble in the optical wavelengths, and that one is seen by far infrared thermal instruments such as Herschel in the far infrared wavelengths. So this is like how it spots the emission of the stellar light, and that one is the emission of dust. And now by eye you can see right, but that one is not as beautiful as this one, and we want to see how this image there, like big circle, can we resolve it somehow and understand what is going on there. And a partial answer to that question is yes. There is another third amazing telescope that is actually not in the sky. It's here on Earth, in the ground, in Atacama Desert in Chile, and it's called ALMA, which stands for huge millimetric array, Atacama Millimeter Array. And this is the same Hubble Deep Field spotted by Hubble Space Telescope. All those blue points here are galaxies, and in some of the cases, and so in some cases, there are some extended emission that cannot be seen by Hubble, but can only be uncovered by ALMA. And ALMA is operating even further in the wavelength range, not even in the infrared, but a little bit more towards the sub-millimeter wavelength. So this is like this window between the far infrared and the radio, let's say. So let's say blue points here are higher energy emission coming from the young stars, and dust is catching that emission, reprocessing in the far infrared, and then you can see this reprocessed emission in the far infrared sub-millimeter, and this is actually what is the emission of the cold dust in these galaxies. And by eye, you can see that non-negligible number of sources can not only be uncovered by Hubble, but also we have to use another instrument to see what is the emission of dust in the interstellar medium of these galaxies. So to complement the picture this small sketch that I showed you at the beginning, it is not just enough to account for the interplay of gas and stars in these galaxies, but we also have to think about dust. And this is quite complicated because playing with both sides in the spectra, it's not easy. So we have to understand physics of let's say young stars, but then also we have to understand the physics of dusty particles, which is very difficult from both theoretical and observational point of view. And one can ask why dust is so important from this principal point of view. So basically dust particles are very small particles, so like micrometer size. They are powerful enough to shape, as I said, this emission coming from the young stars to reprocess this emission in the longer wavelengths. But also dust has another amazingly important role, and because it acts as like a surface of dust grains in the interstellar medium are helping the formation of a molecule of hydrogen. And this is the particular role of dust that it plays in the formation, not only of galaxies, but also like planets and so on. So whoever is a theoretician here would like probably to say, okay, I would like to understand if we see some dust gas coming like as an observation from taken from our telescopes, what are the processes that we should expect happening in a particular galaxy observed with, for example, Hubble or JWST. And don't be scared. So there is a whole like a chaotic mess coming from red ones that are representing dust. And as I said, the dust are we are usually approximating dust in galaxies as something that is made of silicates or carbons. While on the other side you have stars and gas. As you can see in my simplified sketch, all stars are represented by a yellow color, which kind of intuitively maybe reminds you of active stars, young stars, and so on. But fortunately or unfortunately, this is not true for most of the galaxies, because we know that once we observe some galaxy with some telescope, stars, like a formation of stars in these galaxies is sometimes very rapid, like happening at the moment when we observe them, or there are no even new stars produced anymore. For example, our galaxy Milky Way is now producing only one new star of, let's say, of solar mass per year, while in the past it was much more intense. While there are some galaxies that we spotted in the universe, they are producing more than 1,000 solar masses per year. And this is like a huge difference. So some galaxies are very active, and we are calling them starbursts, while the other galaxies are not so active, and they are going to be almost passive and even dead, let's call it. And we want to understand how from this point galaxy passes through all these phases and then ended life as a galaxy that has no these beautiful yellow stars anymore. And on top of that, we want to understand what in the meantime happened with all the dust and gas. And as I said, there is a whole like a bunch of physical processes that we still, I mean, we have to understand all of them. But just if you wonder what are the most important ones, you can maybe remember from this small sketch that there are three basic processes. So the one is called interstellar medium. So what is happening in the interstellar medium of galaxies? Then there is this whole flow of baryons. And then, as I said, there is this cycle of life cycle of dust. Of course, not all galaxies in the universe are dusty. So some galaxies, they don't have this red process as represented here. So some galaxies they have very few or almost no dust. And once you point your optical telescope to that galaxy, you can see if galaxy is massive enough and bright enough, you can see a beautiful representation of that galaxy. But on the other hand, you cannot see. You will see a bit blurry view because dust is absorbing all those photons, and you need infrared instruments to kind of resolve some of these processes. And just for those who are maybe interested in what lies behind in a physical sense, like what are the dominant processes producing and reducing this dust, you will see the one that are shaded in yellow are the processes in galaxies that are producing dust, while the others are those that are destroying. So we believe the dust can be produced in the universe in via different channels, like as a output from supernovae explosions, also from AGB stars, but also dust can, like dust particles can stick to each other in the interstellar medium and grow, like a bubble, and this is called growth of dust particles. Well, the destruction is coming from different shocks, also hot electrons in the very warm gas, and so on. This is very, by the way, I try to sketch it just for those who are curious, but we don't understand even like a single % of this picture. And this is why we had to launch all those expensive instruments to understand it better. But what you can remember from this seminar, and if anybody asks you about why we should take care of dust in the universe, you can maybe remember just this thing, that dust, the total mass of dust particles is only 1% of this beautiful interstellar medium. So you have like stars, metals, gas, and dust is only 1%. But as I said, it has a radical impact on galaxies. And what is dust made of is actually are solid silicates or carbons of this size, like 0.3 to 3 micron to 0.3 nanometer. Depending on how much dust you have in galaxies, you can then count per certain cosmic time that you observe with your telescope, you can count then how much in total newly formed stars we have in these galaxies. So let's say we have this image of Hubble Deep Field. We use the Hubble telescope to observe galaxies in different redshifts, like 0, 1, 2, 3, 4, 5, 6, and blah, blah. And then, if we found that there are galaxies that have this unattenuated view, like these are blue circles, representing what should be visible if there is no dust in them, you can then count something that is represented on the y-axis, and it's called total star formation rate density in the universe, which is basically the total integrated amount of stars forming the galaxies in that redshift, in that cosmic time. And by eye, you can see that it started long time ago with some smaller amount, then it's going up, 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 up. And the peak of this distribution at some certain redshift, which is around 2. And we believe it's not just by chance, because this peak of that distribution corresponds to the peak where we found in the universe most of cold hydrogen gas. But this is if we completely neglect the presence of dust particles in galaxies. If we account for the presence of this dust particle in galaxies, the total star formation rate sometimes is even higher, because you observe, like, imagine that you observe one galaxy with one instrument, and then you measure, let's say, what is the star formation rate in that galaxy only from optical light. But then you think, okay, maybe it's not important to measure the same with infrared camera. But maybe infrared observations will give you even higher number of stars for that galaxy. And this is what this plot shows, that if we completely neglect the presence of dust, we can underestimate the total number of stars formed in the universe in some certain eras. And you can see also that one interesting feature here is that red points are not spread at the same cosmic times as blue ones. This is because we didn't have an instrument to push it further. And this is why JWST is really important. We can now observe dusty galaxies with JWST telescope at even higher redshift that we've seen before. In other words, we will be able to see distant galaxy and also to detect is there a dust in this galaxy. And just to compare some technicalities between the largest space telescope, you can see on the top is the first generation of infrared instrument launched by NASA in 2010. It's called Spitzer. This telescope is still in space, but it's not fully active anymore. And you see this small tiny thing on the right is the size of the mirror of Spitzer. And then you will see in the mid of this image, you see Hubble and the size of Hubble's mirror. And then, which is 2.4 meters, by the way. And then this goldenish hexagonal structure down there is the primary mirror of the Webb telescope, which is more than 6 meters in diameter. And this is largest ever sent into space. And if you watch how it was launched last year, you maybe follow how all this automatic process of unpacking the mirror and also the whole umbrella covering that mirror from the sun radiation went on. And so you can now ask, okay, but why we spend so much money doing all these things? So the answer is to obtain something like this. So basically, this is the typical electromagnetic spectra of galaxies. On x-axis you have observed wavelength, and on y-axis you have, let's say, flux density. And in different colors you will see different regimes of observations. And the one that is important for us, let's say, is the one representing stellar light, which covers this UV optical near infrared part. So this is what we can see with Hubble and Spitzer telescope. While this part that is yellow and green is the one where dust starts dominating. And just to put this in another way, you can see from the physical sources which ones are the most dominant ones. So you have like ionized gas dominating in these shorter wavelengths, like higher energies, and then the reprocessed emission of dust by silicates and carbons and so on in the longer wavelengths. So we can then run the same picture, the same simulation, or a similar simulation, let's say, that I showed you at the beginning, which is not Illustris, but this one is called SIMBA, because there are now simulations accounting for the presence of dust inside. So it's not like a few years ago we only had like a simplified cosmological simulations starting from dark matter, and then we put the distribution of galaxies inside, and that was it. But now we have the whole physics simulated inside, and there are simulations actually telling you what is the amount of not only of number of galaxies, but also what is the amount of stars, dust, and gas in them. And so I'm happy to present this because this is made by our PhD student, Krzysiek, who is not here, I think. But so he made this in one of the largest volumes simulations. It's called SIMBA. And what is the difference between this picture and the one that I show you in the first movie with Illustris is that each galaxy here actually contains dust simulated self-consistently, which was not the case in this older generation of simulations that I showed you at the beginning. So this is one particular example showing one of the most massive clusters in this simulation, and then like a zoom out to see the whole, like a network of filaments connecting and so on. It's a complicated picture, but if you just want to take a look at some certain region inside and to ask, okay, if we just take few galaxies from that simulation, which nicely represent what we saw in the real data, you can see three different things. Not only looking at the images up, but also you can see how different are their distributions of fluxes. Basically, this lower panel is representing this. And if you remember, on the left you see more dominating stellar light, on the right dust. And you take a look again on these galaxies. You can see that in some cases this red curve that is representing dust is start to be very bumpy, like it goes up a lot, which says that this galaxy is very dusty, and that we cannot simply take optical telescope and look through the dust, because it's the central emission of stellar light is hidden. And this is exactly what is represented with this left image cutout that you can see. This sign DSFG is actually, it stands for dusty star-forming galaxy. The same is not true for the other one in the middle. As you can see, this is a blue one, beautiful. It has like these spiral arms with those sparkling points. And the stellar light and the dust light is kind of equal. While the one on the right is what is called red and dead galaxy. This is like just a funny acronym for passive ellipticals, like the most massive elliptical galaxy we see in the local universe. And this is how one of those look like in simulations, but also in the real data. If you remember, like 3 years ago, there was this first image of a shadow of a black hole, right? And Event Horizon Telescope took that image, pointing towards the one of the most massive ellipticals, and that galaxy looks like pretty much like this one, like the one on the right. So these galaxies are not forming new stars anymore. So what we want to understand, how the life of galaxies changes from the left to the right. And so where James Webb now contributes to this picture, so you will see this shaded view, this shaded light representing the range of wavelengths where JWST is contributing. So it's basically starting from 600 nanometers to 28 microns. It's a very large window of electromagnetic spectra that you can cover with a single telescope. It's amazing. And this is why JWST, the cost of developing JWST was like more than $10 billion. Because of these sophisticated instruments that are very hard to build otherwise. And I will just show you this promo video. That is amazing video made by some graphic artists in the STSI Institute comparing Hubble and JWST.
Together, they will help answer some of the most fundamental and inspirational questions that we have about our universe.
Okay, so to sum up this technical part a bit, also one common mistake is that many people believe that JWST is solely developed by American Space Agency, which is not true actually. So it is a big collaboration between the European one, Canadian one, and NASA. As I said, primary mirror of JWST is 6.5 meters, which is the largest one sent to space. And the telescope is equipped with two different types of instruments. So the one category of instruments is made to operate in these optical, or actually near-infrared wavelengths, while the others are specifically made for detecting the dust. And these are like mid-infrared instruments. JWST is now located in the so-called L2 point, which is 1.5 billion kilometers from Earth. And the interesting technological solution is that it has different sun shield layers to actually protect the thermal camera from the solar radiation. And yeah, and many other technical aspects that I'm not going to go through now, but you can read it in the JWST website. It's really fascinating how, from the engineering point of view, how they develop all the stuff. And and finally, we now can enter this new world of explorations and galaxies that James Webb Telescope is contributing. So what are the first results that 1 year after the launch of James Webb we have? And what is the, how can we explain some of the first results? So I will again put this small movie just to remind you how it can be used as a cosmic machine, as a redshift machine for distant galaxies. Okay, and after the first light from James Webb was released, we saw this amazing comparison in the deepness and resolution of Webb images. So you can compare the best view in the same wavelength range that we had so far with other space telescopes, like WISE or Spitzer Space Telescope. And then on the right, you can see just some small, very short single shot made by JWST and how it resolved all the plethora of dusty galaxies and stars in the small patch of the sky. Of course, difficulty is analyzing this data, and one specific thing that you can do with combining near-infrared and mid-infrared observations with James Webb is that you can say something about light and chemical composition in that shorter wavelength side, which is on the panel above. But then you can also say something about the significance of these dusty particles, like silicates. And this is illustrated in the lower panel. So you can see like lines coming from iron, sulfur, neon, and so on, colored in the upper panel. And on the lower one, you can see the significance of silicate, which is dust emission in the mid-infrared spotted by James Webb telescope. So this particular image and this spectra is the real one, and it is actually a composition of a gas around one of the most massive black holes in one of the nearby galaxies. And the composition of that gas is now completely revealed by these two spectral images. And and if you want to see how James Webb telescope delivered the new view of the same galaxy world that world has been seen by Hubble telescope some time ago, you can now compare these two images. So the one on the right is something that we already more or less knew about from this shorter wavelength near-infrared observations. So this is like the stellar emission coming from these galaxies. But now, with the same instrument, you can compare the significance of the silicate emission and emission from hydrocarbon molecules as like a dust emission in these galaxies, which is illustrated on the left. So same galaxies are on the right and left, but some are missing. Actually, a lot of them are missing. And this kind of just qualitative comparison can tell you what is the fraction of galaxies that in the single patch of the sky we expect to have dust and so on. So you can see that a lot of worlds are hidden. They don't exist because these are not dusty, or even with JWST maybe we cannot find this world so easy. This is another amazing science question. So how deep we should go to really unveil the dust world in these massive galaxies. And if you want to see some of these distant worlds in a zoom-in view, this is a nice representation of one of the surveys with JWST that is published recently, and some of those small squares on this big image are zoomed in on the right. And they actually tell you that even one single pixel that in some previous observation couldn't be resolved, like we just, if you go back, you see that what we had so far was like combination of these pixels that we didn't know how to resolve, and now we have this view. And this small square is actually telling you an interesting story, that in some cases you have one single distant galaxy in the middle and then some other points that are like bluer, which says these are maybe nearby galaxies, while the red one is supposed to be a distant one, but we have to check, and so on. But you can also see that some other galaxies are like extended. There is some emission that is like doing some sort of like reflecting some interaction and so on. And all these galaxies are projected to reside in the very early universe. So you see like 13.1 billion years, 13.0, 12.6, and so on. So this is like all these guys are spotted when universe was less than billion-year old, like less than a billion years after the Big Bang. And JWST now with this specific instrumentation facility, which is called integral field unit, can not only deliver image of your galaxy, but each pixel can be also attributed to some spectra. and you can see spectra of these galaxies on the right. And by eye, even if you don't know what is going on here, by eye you will see that in different galaxies, the peak in this spectra is shifted towards the right side, and this is this redshift effect that when you see the same peak in different positions, it will tell you about how distant this galaxy is. And finally, dust. So I will finish this lecture showing you the differences between the dusty galaxies observed with James Webb Telescope in the, let's say, local universe against the one that is seen in the very distant universe. So this is like one beautiful example, which is called, you can see above, like NGC, like New Galactic Catalog 1433. This is like official name of this galaxy. And different filters of JWST are in the mid-infrared part. So this stands for MIRI filters. And different colors, starting from blue to red, correspond to shorter to longer dust wavelengths in the mid-infrared, let's say from 7 microns to 28 microns. So this is what is combined here. So these are like observations from 7 microns to 28 microns. And you put like combine image, you combine all these images. The bluer, if the color is bluer, the contribution coming from these, let's say, stellar sources and these hydrocarbons that are related to star formation are more intense. While if you carefully look, you can also see some very red points, red dots. And these red dots are, they correspond to completely different process of dust emission, and we believe that these are like related to the growth of silicates and so on. In the center, there is this very intense, what astronomers believe to be like a supermassive black hole. So it's a very complex picture. And also by eye, you can see, if you just zoom out a bit, you can see that there is a whole network of these blue filaments crossing and interlinking with each other. So the flow of gas and dust, the whole interplay is very complex. So we cannot really understand fully what is going on here, because this is the first time that we observe with such a resolution, such a resolved world of nearby galaxies. But unfortunately, we can not see even a single detail of this in the galaxies in the distant universe, like the one that I showed you before. And this is a very new paper that was published in Science just a few weeks ago. And what astronomers did, these are like led by my colleagues in Arizona University in the United States. They looked at one of these reddest spots that initially was observed with Hubble. And this is this red blob there. They try to follow with JWST and ALMA, and they found that there is some dust emission, but nothing really spectacular at the first glance. And just to show you how like a small amount of details is needed to really make some big discovery. So maybe you will laugh. You can see there is this arrow pointing to some small bump. But actually this bump, even if it's the significance of this emission is established to be around 4 sigma, so it's almost significant, let's say. This bump is telling you a lot of things, because a galaxy that is observed is not like a normal galaxy. It's one of the most distant galaxies, and it's very dusty. And you can ask then, but how it's possible the dust, which is like a combination of these grown condensed particles, how it's possible that the universe was so enriched on metals and dust so early in the cosmic time? And these astronomers found that following this kind of like line, which is called a dust bump or carbon bump in the early universe, you can actually recover a presence of carbon dust in these galaxies. Like this bump is telling you that there is some dust that catch some UV light from new stars. And then on one side, you see this bump in the spectrum, while on the other, you see this absorbed light as a small deepening of the curve. And just uncovering this sort of, using this kind of diagnostic, which is very, you can see, very deep. I mean, they have a sample of several dozens of galaxies, and they cover this feature for one. So it's very painful. It's a very, very difficult process. But even for this one, it says a lot. It says that even less than 1 billion years after the Big Bang, we had some processes we had to understand that they produced dust particles in some enormous amount. And this is a new paper in Science, and one of the highlights of all the discoveries made by JWST. And if you wonder how these galaxies in the most distant universe look like, you can now connect these cutouts from JWST bands with one of my first slides when I show you how dropping, how non-existence of the points in these images actually reflect on the distance of that galaxy. So you see nothing, nothing, nothing in the first 3 shorter wavelengths. Then your galaxy is starting to pop up, and this is the way to measure or to tell you, to give a glimpse of the redshift of that source. And it's established to be galaxy at redshift 12. And if you remember from my first slides when I told you what was the redshift of the most distant galaxy discovered until this year, it was 11. So now you can see that people are regularly discovering galaxies at much higher distances, let's say more closer to the early phases of the universe. So some takeaway messages is that James Webb Telescope is an amazing instrument, but it has to be used very carefully because it's so powerful and can provide a lot of details that our community was not even prepared for all the details. So we have to understand a lot of physics going on. But some great ability of JWST is to observe simultaneously the most distant galaxies, and not only stellar emission in them, but also dust. And by combining these two, we can unveil not only distant worlds, distant galaxies, but we can actually uncover our chemical models correct. Can we predict in our labs in a good way how dust can grow, for example, in the early universe? Can we really follow our stellar evolution models and predict how much carbons, oxygen, nitrogen, and so on, how much it can be formed in the early phases of the universe, or we are missing something? Then number of galaxies. There are already some studies finding much more massive galaxies than what lambda CDM, our current cosmological model, predicts. Is this a tangent, or maybe some observational bias? And so on. So there are many amazing, great open questions that we have to understand in the years to come. And JWST will help us to do it. One great thing that JWST is capable of is to deliver the data not only in the amount of years that was predicted, but much longer. So it was designed, it was supposed to deliver the data in the first 4 years. Now we know that it will be active in the next at least eight years. And one final thing that I wanted to mention is that when I was talking with Barbara before this colloquia, I mentioned that we as an astronomical community always have to fight for this data. So if you see any beautiful image from big telescopes on the internet, don't think that these data are just there. So nobody is really delivering this for free to us. So we have yearly competitions that are happening on some basis. For example, for JWST is now every December. And almost 2,000 teams around the world have to fight for a very insignificant part of this project. So let's say less than 6% of the total astronomical community has a chance to handle this data before they become public. So these data are expensive and precious, and whoever gets this data is making like a big like a breakthrough, and that's why follow the results of JWST, because there will be a lot of surprises, and I hope in the months to come. Thanks.
Thank you. Thank you so much for the exciting lecture. And I guess there are many questions now. Jan, just below you here.
Thank you very much for this nice talk. I have a question regarding the composition of the grain. When you compare the composition of the grain from distant galaxies and let's say our galaxy or galaxies which are close to us, are you able to measure some difference in composition, or do you expect anything? And this is like both the question about the composition itself, but also in our galaxy we have some kind of a layer of ice on the grain. So the question is, are you able to observe also this ice in the highly redshifted galaxies, or it's impossible? How it is?
No, that's an amazing question, and unfortunately, we yet have to understand the techniques to have the to see the presence of different, let's say, grain compositions in the distant galaxies. So the only way to see it is now with the JWST looking at this mid-infrared emission, and then making some, let's say, simplified diagnostic diagrams by comparing the strength of the emission in this shorter versus longer mid-infrared emission. Because we know from our labs, like astrophysical spectra, that the one on the shorter side will be mostly attributed to, let's say, smaller grains, like hydrocarbons, while the one on the longer side is expected to be dominated by colder dust and larger grains. And these larger grains are, if our current knowledge is correct, can only be produced by what you actually mentioned, this kind of stacking process, or how we can call it, where you have some merging of these dust particles in the interstellar medium, and they can grow. But to your question, we have no idea, is this process efficient in the early universe or not?
I have a question about dust. This is a very important component of galaxies. Could you tell us some more about this? You said that dust absorbs UV radiation. Can this radiation be transformed into some sort of work by this component?
So can you please transform to what?
Transform UV radiation into work.
If I understood correctly, well, this is basically how it. If I understand your question correctly, so this is a typical representation of that process. So in principle, what we know is that in massive galaxies, where they have more dust, the stronger is the absorption. And then this left side of this diagram, of this curve, usually drops like more significantly than in the cases where dust is much more shallow, or there is no dust. And by, let's say, combining these two, like the making this picture, we actually, this translates not only to the physical processes in a galaxy, inside the galaxy. But also we can use this to understand the whole distribution of the light in the universe, like which is called unresolved cosmic background, let's say. So by this we can also measure in the universe, like the whole universe, what is the fraction of the UV light, like a cosmic UV background versus dusty one, infrared one. If this answers your question.
Nice, thank you. My question is about you showed some pictures of very old galaxies, and you said that we are able to resolve dust in these older galaxies. My question is, how far or actually how old can a galaxy be and we can still see dust with this new instrumentation?
Yeah, that's
because if I understood right, there's a limit, right? If we see very red galaxies, we cannot see dust on them because it's outside of our limit.
Yes. Okay, right. So this is actually an amazing question. Each instrument has some limit in the capability of detecting some distant work, right? And so maybe the best is to look at this picture, and then by eye, you can try to combine, to attribute one of those galaxies on the right to the one that you see on the left. But in some cases, the red point here can be at the same position as a galaxy on that image and not be the same one. Because basically in the line of sight, you can have some, as you said, like a dust world that is far away. And we have to understand how distant is this world. So far, the most distant galaxy that has dust, like significant amount, and is detected is in redshifts around 7, which is you see, like roughly a bit more than 800 million years after the Big Bang. And this is actually what we want to understand now. Pushing further, so we can go with JWST, we can go to these redshifts of 15, and we have no idea how many dusty galaxies are there.
If you see 15, could you see the dust?
So in principle, only by combining these mid-infrared emission observations with something else. And something else is like a glimpse of emission seen in the longer wavelength instruments, like in the millimetric range. But so far, nobody succeeds to detect this. Yeah. But would be amazing, of course, if it's possible.
Okay, more? Could you maybe tell us also how long is this mission supposed to work, approximately?
10 years, roughly.
And why 10 years? Then
as far as I know, it's not clear yet, because
it's due to what?
At the beginning, they projected it like shorter. And then it happened that the whole like energetics, like the whole small subtle things coming from the engineering side were working amazingly well. And now STSI, Institute in Baltimore, who is in charge of basically mission control, they said that the JWST will deliver the data not only for 5 but 10 years.
Okay.
Yeah.
So if this is only 10 years, that means that the next instrument should be already in pipeline. Is there such an instrument?
So, first thing, it is true that it is only like a decade, but the amount of data that will the already came is it's huge. So we don't have like enough servers to store this data, and also we have to understand how to process this data. And for the future instruments, there are some, let's say, sketches of the future generation telescopes. One is called Nancy Grace Roman telescope that NASA is leading. But in this combination of sophisticated instruments covering both sides of the spectra and basically telling you the two different physical processes in galaxies, we will have no telescope like that in the next at least 20 years. But this is one thing, but as I said, there are others that are going to be launched very soon. Like this July, European Space Agency is going to launch one of the largest European telescopes, which is called Euclid. We are all waiting for this because Europe now has no rocket to do this, so we have to rely on some untested rockets from the SpaceX. So let's see, hopefully it will work. But this telescope will complement what JWST is doing. So JWST, as you saw, it's doing this amazing, resolving these galaxy worlds, but the field of view cannot be so huge, of course. While Euclid will do the opposite. Euclid will have a capability to observe the whole, like a vastness of space around these galaxies, and to give us the estimate of the distribution of galaxies. So we can combine these two to say in which environment most of these galaxies from JWST I show you reside. So you will have like a measure of, let's say, baryons, like also dust, gas, and so on, but also distribution of dark matter in the universe.
Okay, I don't see any more hands raising, so we thank the speaker again. Thanks. And let me also announce you that the last colloquium, beginning of June, will be devoted to artificial intelligence.